Okay, I'm back. Sorry about that. So yeah, so here we have the situation where you know this angle. Everybody seeing the slide, right?
Yes.
So you know this angle here. So everybody see this angle here, and you need to know what is this angle. And what you'll notice is that, so this is the actual expression. It's just a little trig. But to solve for phi, you actually can come up with the algebraic expression which says phi equals some function of alpha. You'll only get phi equals a function of both alpha and phi again. No way around it. And so it's an example like this in which you can use iteration to determine the angle. Alright? Okay. So now iteration has two general categories. One is called root finding and the other is called fixed point. Root finding and fixed point. So root finding is when you have an expression. Let's write back what we had before. Remember I had this g of x equal h of x. So I could change this expression to say g of x minus h of x equals 0. And what root finding is just going to say is find out when all of this, what is the x that gives us 0. Okay, it's still the same solution to this problem. It's called root finding. Okay, fixed point finding is saying let us solve for one x in the system. For example, if I go back to the problem we just looked at, so I could say I'm going to solve for alpha, or for one of the phi's. So let's say I'm going to solve for this one. So I would simply write it like this: R2 cosine phi is equal to R1 cosine alpha plus R3 minus cosine alpha plus phi. Everybody see that? And then I would just say I can erase this, and then I can put it over here. So this would now be divided by R2, and then therefore I would just say phi is therefore equal to the R cosine of all of that. So now this is called the fixed point option, where we say the variable you're trying to solve for is written in the form of a function, and in that function is still the variable that you're trying to solve for. Okay, that's a fixed point form. So that's what this is saying. The variable I'm solving for is written in a form where it is equal to a function, and in that function is the variable that I'm trying to find. So this is where the guess is going to be put, and this is where the answer is determined. And if the answer is the same as the guess, then the guess was good. Alright? In this case, we also guess. We guess for x, and we see what answer we get. If we get 0, we say we're good. If we don't get 0, then we say let's try again, and so forth. Alright? Everybody following?
Yes, sir.
Okay, good. Alright, so every iteration has two stages. Generally, first stage is to guess. You have to start with a guess, and you have to refine, which is like the trial. So trial and error. Okay. Now, whenever you guess, you can guess in two ways. You can have a bounded guess. That means you know your answer is in a range, or you can guess a point and say, I'm going to guess this is the value. So you have two ways to do your guess. You say, my answer is somewhere in a region. That's one way of guessing. Or you say, my answer, I'm not sure, but I'm going to say, this is my answer. It's actual what point. Okay? Let's talk about guessing some more. So how do you normally guess? Whether you're bounding, everybody should be clear on bounding. Let us say I have a function. So I'm going to draw a graph of a function. This is a function of x. I happen to know that this is my function in this case, but I'm just using it as an example. So bounding says I know my answer is between here and here. That's how I bound. Okay? It's called bounding. That's one way in which you establish your initial guess. Or I could alternately say, I'll guess another way. I'm going to say this value is my initial guess for x. Alright? That's a guess which is unbounded. When you do the unbounded guess, I'm going to get a solution. For example, I'm doing the case for finding a root point. Okay? So here's my initial guess, and for this guess I find that my function is not 0, my function is this value. Okay, so what iteration does? It says make another guess. If it's an unbounded case, your other guess can go anywhere from negative infinity to positive infinity. There is no restriction on where your second guess goes. In bounding, however, I start with these bounds, and using these bounds, so I'm saying my x must be between here and there. I must know what bounding does is I'm going to now decrease my bounds as time goes on until my bound reaches here and there. Okay, so those are the two ways in which you bound your system or you perform your initial guess. Remember, bounding limits your answer to a region, while unbounding allows your answer to possibly be anywhere. Okay, how do you normally choose how to bound? That means, how do you start your problem? You need to have an initial guess. We should all appreciate that we never truly guess. Everything is educated, right? Our guess is never truly a guess, like a shot in the dark. Everything is educated. That means there's a basis for every decision that you make. So guessing sometimes starts off by graphing. I just did a graph, for example. The graph doesn't give you, for example, I may graph a function. Graphing must means I find that a few points. Okay, this is not iteration, guys. What I've just did here, when I do a few points, this is not iteration. Okay, it's not iteration. That's making a graph, and from the graph I say my answer seems to be somewhere around here, and so I base my initial guess on a value that is close to where it seems the root would be. Okay, why isn't this iteration? Because each one of these calculations, I am not improving my answer, I'm just getting a set of information. Okay, the second way you can start guessing, or you do the initial guess, is incremental. This is also an example of incremental. It's not exactly the same thing. Here I solved for a set of information and made a graph, and then I interpreted the graph. What is incremental? Incremental is to do this instead. Incremental is to say I am going to step through a system. So I'm going to go from 0. Let's say my answer is somewhere between 0 and 100. Okay, so I'm going to solve at 1 and 2. These are not guessing. I want it to be clear. There's no guessing here. What I'm doing is incrementally going through the whole thing. After incrementally going through, I find where it seems I'm closest to 0, and then using that value I start doing my iteration. Okay, that becomes my initial guess for my iterative procedure. Another way we can determine an initial guess is using past experience.
Can you repeat incremental search, please?
Okay, so let me repeat incremental search. Incremental search is an example I just gave. Let us say my variable, I know my answer is greater than 0. It's not bounded. A graph, if I'm going to use a graph if I'm going to go with the first option says take some points, plot the points, see where it looks like it's close to 0, and then you start doing your iteration using a value close to where it seems it's 0. Understanding that the graph doesn't give an exact answer. Okay, the graph just gives you an approximation of about where the 0 is, and then the iterative procedure will give you the exact answer. That's graphing. Incremental usually is one-sided in terms of your bounding. So while a graph, you say I'm going to graph between 2 points, incremental says okay, I am going to, let's do it another way. Incremental says I know that my information or my answer is greater than 0, or let's say greater than 100. So you say okay, 100, find the answer. This is your answers. You check. Let's say I'm using the root point method. Do I get 0? Or you check what answer you get, okay? And then you go 101, 102, 103. What I'm trying to say is these are not guesses. What you're doing is you're incrementally going through a set of information, not iteratively but incrementally. And a time will come in which you realize that your value, your solution, which was changing, will, let's say, approach 0. It might say 0.5, and then this is negative 0.2, and you said, here is where my answer seems to lie, between 104 and 105. So you use your incremental search to come up with your initial bounds. Understand?
Yes, sir. Thank you.
Alright, good. Next one, past experience. Give you an example. Let us say you are trying to determine the power that you expect to be. Okay, let's say the load, the demand, electricity demand for a certain facility, you need to predict it, and it's going to be based on several variables. Okay, and all those variables all come into a function that tells you what electricity demand is. You can't actually solve that complicated function for electricity demand. You're going to have to guess what it is, plug it into the function, and see if it works. What you can do is you can say, well, yesterday the electricity demand was a certain amount, or last week Sunday, let us say it is tomorrow that we need to determine the electricity demand for. So you can say, well, last week Sunday electricity demand was this, so I'm going to use last week's electricity demand as my initial guess to predict tomorrow's electricity demand. That's what using a past experience is like. Alright, next option, using a simplified model. Let's say, okay, so I'm a energy person. Even though you're not all energy person, you may know of the ideal gas. An ideal gas is a type of gas. Nothing is really ideal, but many things are approximated as ideal. And so let's say I wanted to determine the property of a gas. One of you all call me? Oh, I'm in a class. Two more hours of okay, it wasn't one of you, sorry. So yeah, so let us say you want to determine a property of a gas, or yeah, a property of a liquid or something. The actual property is the liquid itself is a very complex system, and it has a lot of factors that affect its property. It may have a solute versus the solvent, and you know, the concentration and the temperature of the liquid, and the pressure and so forth, you know, a lot of different things. But what you would say is, let me assume the liquid to be water, and let me assume it to be what's called an ideal liquid, and let us assume it to be something, and you use that to determine the initial whatever you want, let's say density. Okay, that is going to be your initial guess, and you're going to use that now in your more complex expression to determine what the actual density is. Alright, so the ideal would be the simplified solution, or your initial guess, and then you improve based on your more complex relationship. And lastly, previous solution in a sequence of solutions. This is sort of similar to past experience, not exactly the same.
Sir, can you explain the previous one, simplified model?
Again, simplified model. Let's do it again. Simplified model. Okay, let me use the ideal gas. No gas is truly ideal. Let us say I want to calculate the density of a gas. The equation is density. Oh, what was that? Hold on. Let me erase everything on the slide. So the equation, ideal gas equation, is density is equal to P over RT. This is ideal for ideal gas. Okay? So let us say I need to calculate the density of a gas. In reality, the density might be P plus Density squared over alpha or over A divided by R plus T times the exp of E over RT. I'm just giving you some complex thing, okay, where you want to now solve for, let me make it a little bit more complicated. Alright, and now you need to solve for this density. Alright, to solve for this density, you can't solve this expression for density, it's too complex. Understand? So that's why we would use iteration. Now what would you use for your first guess? You would say, okay, I'm going to assume it's an ideal gas, and then I will use the density from the ideal gas and plug it into this value here and continuously improve my guess until this density becomes the same as what I plug in. Did that help? So this is the simplified approximate model, and this may be the real model. Hello?
Yes, sir, it's clear.
Clear? Alright, good. Thank you. The previous solution in a sequence of solutions is similar to the past experience. Okay? Yes?
If you can use the ideal gas law.
Yeah, go ahead.
I'm saying, if you can use the ideal gas law and find the density, why do you have to iterate it to prove that density?
No, you see, the ideal gas law is not true. The ideal gas is an approximation. Let us say you want to find a real density. So you start out with an approximation. Okay? That's what I'm trying to say. The ideal gas law, even though we use ideal gas law, it's not really, no gas is truly ideal. It's just an approximation that is sufficiently accurate under some circumstances, but not necessarily all circumstances. Understand what I'm saying?
Yeah.
Okay. So when you want to calculate the density, if you use the ideal gas law, yes, you'd get a density, but it would have an error. Not saying that it is an illegitimate density that you calculate, but it won't be exact. So your for example, your material may have what's called a more improved equation of state, not the ideal gas, but something that is more precise for the gas. So, but you can't solve it algebraically, so you're going to have to use iteration to calculate the density. And so remember, to iterate, you have to actually have an initial guess. So we say, okay, we use the ideal gas as the initial guess, knowing that it's not correct, but it's close, and then from that you can improve until you get the exact answer. Alright?
So is it that we're going to continue to solve, iterate it until the degree of error
goes down? Yes. The degree of error is simply this. Whenever what you plug in as your guess, or whenever what you solve gets close enough to what you plug in as your guess, then we say we have converged on our answer. Okay?
Okay.
Alright, good. And yes, I was saying now, the previous solution in a sequence is similar to past experience, but it's not exactly the same. It may be that I'm solving a system or a set of equations. Let me give you an example. So I may be solving an equation that says, for example, x squared plus a natural log two x equal cosine x. That's a crazy expression. I don't even know if it's solvable. Now instead of writing where a, we want to know where a is equal to 0, 0, 0.1, and so on, all the way to 1.0. Alright? This is an example. So what do? After you solve for the case where a equals 0, that means where this doesn't exist, it's where the case where a equals 0, you're going to get a solution for x. That's x for a equals 0, and you'll get your answer. I'm going to call it a0. Okay? So you actually get your answer. Now you want to know x for a equals 0.1. How do you get that? What you're going to do is you're going to use this value in your iterative sequence as your initial guess. Okay, so it's a sequence of solutions. So what we're going to say is probably the answer for a equal x equals 0.1 is not very far from the answer for x when a equals 0. And so we use that as the solution for x at a equals 0 as your initial guess for the solution of x at a equals 0.1. When I've solved for x where a equals 0.1, now I can go to the next problem, which would be x when a equals 0.2. And I can say probably it's not too far from the answer for x when a equals 0.1, and so on. So that's what we're saying, using the previous solution in a sequence of solution. That's what that would mean. Okay?
So the guess now would be the solution of the previous solution.
Yep. See, previous solution in a sequence of solution is the initial guess for the next iterative solution. Understand? Hello?
Not quite.
Not quite.
Repeat the part again, sir.
Alright. This is a real problem. When I say problem, this is a real scenario. Let's say I wanted to solve this expression. Alright? And I want to solve it for these cases. All the way down from a equals 0 to a equals 1, increments of 0.1. So I'm going to solve it first for a equals 0. I need to solve for x. So do my little iteration. The very first case, that is for a equals 0, I cannot use the previous solution option for my initial guess, because I wouldn't have had a previous solution to work with. Is everybody clear on that?
Yes, sir.
Alright. So that's my first iterative sequence, and I would have solved for the first value of x. That's x when a equals 0. Now I need to go to find x when a equals 0.1. Now I'm doing a sequence of solutions. So what I'll do is I now go to a equals 0 use the answer I got when a equals 0, and I'll call that my initial guess for finding the value of x when a equals 0.1. Lot of terms. I hope it's not confusing you too much. Give me some feedback.
The following.
Alright?
So all this is to, like, x is going to converge to the true. That's what you're saying, right? X going to converge.
No, I want you to understand these are all different, completely different solutions. So this is a case in which I want 10 different solutions, or 11 different solutions. A solution for a equals 0, a solution for a equals 0.1, and so on. But every time I need to find mute. Thanks. Every time I need to find a new, remember these are 10 different solutions I'm trying to find. Okay? The 10 solutions are not 10 steps of an iteration. Okay? Each solution itself will have its own full set of iteration. But for the 10 iterations, I would have used the previous iteration to help me to start off the next iteration. The only one in which I will not have used a previous iteration is the very first one. Okay? And it could go either way. I could have started at a equals 1. And I say, okay, now after I solve for the answer when a equals 1, I'm going to solve for the answer when a equals 0.9. And I would have used the answer I got when a equals 1. I'll use that as my initial guess for the case where a equals 0.9, and I step down to a equals 0. Okay, each being its own full solution. So it is not one solution, it is a set of solutions, each having its own iterative procedure and each requiring its own initial guess. But in all these cases, the initial guess is assisted by the fact that I did a iterative procedure using almost the same expression previously. So I'm going to use that to help me for my next iterative procedures initial guess. Alright?
Sir, is it safe to assume that it is similar to the incremental search?
No, not. It is better saying it's safe to the past experience. Okay? Incremental search is you start somewhere. It's not a guess. You start somewhere and you change incrementally until you get to a area that looks like it's close to 0, close to the answer, and then when you get to that area, then you start your iterative procedure. So the incremental search gets you to the initial guess. Alright?
So this is the first step to the incremental search?
No, this has nothing to do with the previous solution is not the incremental search. They are not the same thing. But I said the previous solution, this fifth way of doing guessing, there are 5 ways that I'm saying here. 1, 2, 3, 4, 5. Case 5 is similar to case 3, but it's not the same as case 2. Okay?
Okay.
Alright. So that's, remember I said there are 2 general stages in iteration. The first one is the determining the initial guess. So that's what all this discussion has been about. The next part of the procedure is refining your guess. or now we talk iteration. Alright, again, incremental search is not iteration. It is how to get to the initial guess. After you got into the initial guess, then you'll start doing the iteration. So you can iterate several ways. There's another type of trial, there's another term which we call trial and error. This is not going to be discussed here. Trial and error means a shot. In this case, it means you have a, let's say this is my bounds. Let's say I know my answer is somewhere here, and I try and I try and I try and I try and I keep going around until I find the answer. That's what we call trial and error. We are not, that is not a mathematical or engineering approach to getting a solution necessarily. Okay, not saying it doesn't work, but I'm saying there isn't any analysis. There's not analytical basis for that procedure, and so we will handle it in this exercise. All right. So what we are dealing with now are these two general options: the closed domain, or we call bracketing methods, and the open domain methods. Note, the bracketed methods are the methods that utilize a bound for your initial guess, while the open domain methods utilize a certain point for a point on a spectrum for your initial guess. So let me say that again. The closed domain, you limit yourself between two values of, let's call x the unknown, solving for x. So this is x, and here is x. Closed domain says x is between here and here. That's actually, these 2 points become your initial guess. The range is your initial guess. Okay? While the open domain is a point, is your initial guess. Alright? Point, sorry about that, yawn. So the point is your initial guess. So these are the two ways of so based on what your initial guess is, it tells whether or not you're going to use a bracketing or an open domain method in refining your search. Remember, the two parts to our iterative procedure are the initial guess and the refining. Okay? Refining ends when the error is small enough to be satisfactory, and small enough is a subjective thing. It depends on the purpose of why you need the solution, right? So small enough for one person may be different for another person. What is small enough for one person may be different from what's small enough for somebody else. Alright? Okay. Now, iteration has its issues, so we want to discuss what those issues may be. First, one big problem with, I wouldn't call it a problem. Probably I should change the title of this slide, and not call it a problem. But yeah, there are concerns, or there are issues that you have to address, or things that you have to be careful about.
Limitations.
Okay, call it limitations. Nice. Limitations with iteration. First, you need a good initial guess. So you see, if you ever started a guess and it is far from the reality, you may never get to the answer. Or you're not looking in the right place. It's like searching for something. Alright? If you're searching for something, let's say remember that your guess is educated, right? Like the other day, I was doing something. I was hammering something, and I'm a slip, lick my finger, bust my finger, right? So somebody there flash my hand now. Flash my hand. While me I flash my hand, me flash off my ring. My wedding ring. And I'm outside. Wedding ring drop on the grass. My children are out there. And one of them say, me hear it lick on the wall. I hope you understand. Hearing it hit on the wall helps to inform the initial guess. And somebody say, me see a little flash. That is when the sun lick it and it flash. And so now they're now going to have to find where that ring is, right? And so we have to do, I mean, I'm just saying it's a natural thing. So your brain kind of kick in and it start saying where is the right place to look. And it thinks if you hear it hit a wall, then there are a few options. You look around and you try to see where the wall is, and then you say, one of the children said they saw it flash. Might be a crazy thing, but you say, where's the sun coming from? So the sun is over there, then he couldn't see it flash because the angle of the sun would make it flash. You know, I'm not saying that I thought those thoughts directly, but what I'm saying, that's really how an initial guess comes to play. But eventually one of them say, I think it's over here, and him go and he start go through the grass and go through the gravel and he find it within 10 seconds. I actually didn't even think it could be found so quickly, but it helps you to appreciate how important a good initial guess is. Now suppose we never have the wall, the ring didn't hit on a wall, and suppose it was a dark time or a cloudy time, so there wasn't any hint of a flash of anything, so nobody would know, nobody heard anything. We just know say it drop off of me and wouldn't have a clue where to start looking. And then so we might just say, okay, let me start looking over there. Bad guess. And I might be there all day, all night. Wake up the next day and I don't know where it is. So you understand that's an example of what an initial guess, how an initial guess is important. And if you have a bad initial guess, you can have a bad initial guess, and that causes you never to get to your answer. Okay? Am I clear?
Yes, sir, but just confirming, the initial guess supposed to cut down on computation time, or it can determine whether the answer is there or not?
Both.
If you understand what I'm
Yeah, man, both.
Both.
Sometimes your initial, okay, your initial guess can cut down your computation time, but for a computer, if it's not a human, it's a regular computer, that may not be a very critical thing because you can go through it quickly. Okay? But if it's like a very complex problem, then a proper initial guess can save you quite a lot of time. If the computer has to do, let's say, millions of procedures to get to the answer. So a good initial guess can make the difference between minutes or days in solving something. It also, Jordan, impacts whether or not you get to the answer. So one, it can cut down the time, and two, it can actually determine if you get an answer. Alright?
Okay.
Secondly, there is an unpleasant reality. Some iterative procedures by nature can, not must, but they can go away from your answer. Okay? Or they can not converge. No matter how close you are, you'll never get to the answer. And it's not a problem with the guess, it's a problem with the procedure that is chosen. So we're going to look at some procedures and see what procedures must get to the answer versus procedures that may, what we say, diverge from the answer. Okay? Thirdly, a third problem with iteration is that sometimes there is no answer. Alright, there is no answer. Using the ring case as an example, let us say the ring drop off of my hand, and I say, alright, I go there the next day and look. Oh, and during the middle of the night, you know listening? So during the middle of the night, one rat come and swallow it and gone. Next morning now, I go there and say, alright, I go start look. There's no ring there. But I'm looking for an answer where there is no answer. Understood?
Yes, man, I understand.
Alright.
Yes.
Last case, many answers. Let us say I dropped, not a ring, let's say I dropped a stone. I dropped a stone on the ground. And I need to find the stone. I better find a criteria that establishes that it is this stone that I'm looking for, because I'll find many stones and I want to know which is actually this stone. So sometimes you can have more than one answer. Alright? And iteration really doesn't. Sometimes iteration never tells you if you have more than one answer. Iteration will just bring you to an answer if it does. And when you get to the answer, you hope that it's the answer, but you better have some other information or some other criteria that will help you to assess whether or not you're sure that this is the answer that you want. Alright? So here are some examples. Somebody want to ask a question? Somebody just
In a case like that where you say you drop out for one stone, but there are many stones in terms of your answer, and you need condition now to identify the specific stone that you're looking for, because the iteration won't give you that.
Yeah, alright. Unmute.
What kind of
No,
condition you say? For example, what is the example you gave? What kind of condition you could put to that stone to say, well, this is the stone? You have to put that condition before you drop the stone to identify it.
Right. No, so you'd have to put the condition before you choose your function that identifies the stone. So for example, you might say I'm looking for a stone, and in looking for the stone you use as a criteria a white object of a certain volume. Okay? And so I tell my son, go find a white object, and I show him what size it should be, and he goes out there and he sees 10 of them. What he's going to do is he'll grab the first one, let him find. He won't see 10 of them, he'll just see one, because let's say him can't bother, him too lazy for work, or him too lazy to carry the 10 of them. So he just grab the first one and see, and run come back with it. It may be that I gave him a poor criteria, so I may change the criteria to say white stone, this size, and a certain mass. Right? Because let's say the stone I want is a special stone and a certain color, and so that can help so you have to, whenever you have multiple solutions, you have to know increase your criteria or make the criteria more specific so that you can eliminate the several solutions to the one that you know you want. Understood? Paul? I think that was Paul, right?
Yeah, I understand that part. But you say something that in terms of the specificity, you may have cases where you have to increase certain criteria versus in some cases you might have to minimize it to make that selection.
No, you always increase criteria to reduce your number of possible solutions. So you use more criteria to reduce the number of possible solutions. Okay? So suppose me say I want the fat man. A fat man. Just say fat man, you have buck up and whole heap. So you say you increase the criteria. Fat man, a black fat man. And it will reduce it. But it won't narrow it down to one. You say black fat man a certain height and reduce it a bit more. You understand? Increasing the criteria reduces the number of possible solutions. So you make up, and the other thing is, it's important sometimes that you run the iterative procedure. Make sure you understand your iterative procedure or your system, so that if there are several solutions, find all the solutions. So you may have to repeat the iteration, starting with different initial guesses, because a different initial guess will give you a different solution. It's like searching for something on the ground. If you start your search at a certain place, you'll find one, but you're not satisfied that you found what you really want, so you start somewhere else and search again, and you may find another, and you find several. Understand? After finding the several, then you're going to say, okay, I need another criteria now to eliminate some of these. And you might add a criteria and it eliminates half of them. And you say, I still need another criteria. So you add another criteria, eliminate another half of the half. And you keep improving your criteria or increasing your criteria until you've identified the one now you're sure is the answer. Alright, Paul?
Yes, sir. Clear on that, sir.
Okay. So here comes. Yes.
This is just for the initial guess.
No. This is for the solution. You can get a solution. You make an initial guess. Initial guess gives you a solution. But if you change your initial guess, you may get another solution. So sometimes you have to know if your system has more than one. You may not know that what the answers are, but you know that the system has more than one solution. For example, a quadratic equation. You see this plot here? These plots here? KC is a quadratic, right? But you know what a quadratic equation is? It's
Yes, man.
Alright, so y equals ax squared plus bx plus c. And the rule so the rule is that if you have a quadratic equation, it's likely that it has two roots. That means two places where the function equals 0. So let's say the quadratic equation is a way that let's say some physical system, when it is being expressed, is in the form of a quadratic equation, and you want to find the solution. You have to understand there are two possible answers that will come out when you're solving for this physical system. Solve for the two of them. Know that it's two, but then when you see the two, then you'll be able to say this one is not the right one, this one is the other one is the correct one. Understand? For example, if your system, let's say you're calculating mass and you're using some model, and in the model the mass turns out to be a part of a quadratic expression. And when you find the mass, you get two answers. One of the masses is 3.2 kilograms, and the other mass is negative 2.9 kilograms. What do? You say mass can't be negative, so therefore the 3 is the one that you go with. Understand? Suppose you had done the calculation and you got the negative 2 point whatever before. That was the first one you got. You don't jump on it and say, aha, I found the answer. you would have appreciated your second criteria, which is mass can't be negative, and there may be other answers, and so you repeat the question until you have identified all the possible answers and the one that must be the more reasonable answer based on the physical laws of your system. All right. Who did ask me that question? I want to know if I'm clear.
Sir.
Yeah.
Just want to clarify something. I was watching a video some time ago, and the person was writing a program, and when they run the program, for example, they may run it 5 times, and they get an error, and then they run it again, and they get a solution, and they run it 3 times, and they get an error, so the pattern of the errors were random. So does that stem from this, what you explained to us now?
They got different solutions sometimes.
It's more of an error. So they get an error, and then when they run it again, they get a solution. So the pattern was random.
Okay.
So they'd have to write something in the program to say whenever you get an error, wait a certain time, try to check before you go ahead, something to that effect. So what they're explaining to me now, to me, kind of seem along the same line. So that is what I want to confirm with you.
Okay. Let me give you an example of where that is possible. Let's say you have a function like this. I'm going to draw a function. This can be a real function. Please note, you can have a function that looks like this. The dashed lines are asymptotes, alright? Everybody understand? And these are the axes, X and Y. Everybody see that? Everybody clear?
Yes, sir.
Alright, and so let us say you want to solve for the root. There are 2 answers. Those are the answers. Probably it must be a positive answer, so this is really the only legitimate answer because it's a negative x root. Alright, somebody runs their iterative solution, but they started a guess right here, and when they start the guess right here, they keep going on this leg or on this in this range, and in this range they never get to 0, so their procedure that they use may actually say no solution, and they might go over here and they get no solution, and then they might go here and they no solution mean error, or they might go here and they get a solution, and then they might go here and they get another solution. So the initial guess impacts what the solution is. Note, whenever you put in the exact same input parameters, you can't get different outputs. Okay, you always have to get the exact same input. The only case in which you can get a different output from a solution, from a procedure, is if somewhere in that procedure there is a clause for random number generation, because random allows for difference. Okay, so that means when I run the procedure again, when it comes to the random number, some different possible number may come up. So unless there's a randomization function in your procedure, every time you repeat a procedure, if you use exactly the same initial guess and it's the exact same system that you're solving, you must get back the same exact answer. Okay, so the only time in which somebody, if they repeat a procedure, sometimes they get something, sometimes they don't get something, the only case where that is possible is that they start with different initial guesses, or they slightly change their function, or they change their function, whether significantly or not. Even the most insignificant change can result into a significant change of output. Alright? So, note all these different possibilities. Oh, somebody wants to say something? Somebody wants to say something? Alright, come.
No, sir, finger was slipped.
Alright. So here are possible solutions. First of all, I'm going to go through this quickly. Case A, one solution. Case B, no solution. Okay, so I want you guys to know, chime in now. Case C.
Two solutions.
Right.
Yeah, two solutions.
Right. So you may do a procedure. The truth is you're not seeing a graph, you're just seeing an equation. And by the way, it doesn't have to be some quadratic, so you know that there's two solutions. Maybe some very complex thing. But the point is, you can have a system where you have more than one solution, two solutions. Case 3.
Sir.
Yeah?
Sir, question. Suppose you have one of those equations that may not be a quadratic, but it has two solutions, and you get one answer that's not the right one, that does not seem too wrong.
Yeah.
How do you you just guess again and to see if you can get at the next route there? What's the procedure in that
Okay,
case?
so that's, okay, this part, these cautions are now dependent on your knowledge of your field of study. So I can't tell you exactly what you should use as a red flag, because it all depends on your field of study. Understand? But you can also help, you can generally understand some of your answers if you have some general idea of the trends. Let me give you one example. It may not be a quadratic, but it may be a case where for very large x's your function is large, and for very small x's your function is also large, like a quadratic. In such a case, if you found a solution, then there must be two solutions. Understand?
Yeah, continue.
Another thing that can help you to find out where the second solution is you look at how the line passes through y equals 0. That means, is it sloping up or sloping down? When you find the first one, then you can say, is it sloping up or sloping down? If it's sloping up, then that means your other solution is going to be to its left. And if you're sloping down, then that means the other solution must be to its right. Understand?
Yeah, I do.
D, case D. Obviously,
3 solutions.
problem with a case D can be mistaken to be a case A, because it's on one side large, that means large x, large y, and on the other side it's small x, small y. So you get a root and you say, you think it only passes through y equals 0 only once. Understand? Hello?
So, yes, sir. So, the slide that you were talking about before, where we had the different iterations before you refine.
Yeah.
Case A could be one of the initial iteration, and then case D could be a refine where you see more solution.
No, you see, if you solve and you solve and you find A, believe it or not, you're stuck. A will never give you any answer but A. That means if you find one solution, because it's the same system, it will keep giving you back that solution. The only way you can get a different solution on the same system is change your initial guess. And your initial guess now can't be it can't be the answer you got before. You have to use another initial guess. And you can't use the initial guess you used before either. You hearing me?
Yeah, I'm hearing it. My favorite, sir, is if a case D look interesting. It's if the initial iteration that you're showing me, just chop up that graph, how the initial would have looked. If you can,
actually, yeah, we're going to deal with the procedures soon, you know. These are just what do you call it, scenarios. But we're going to actually do that, and you'll see how those work out. But let me humor you for a bit. So let us say you did your procedure. You found a solution. Let's say you found this solution. Again, you must know your field of study, and you must have an appreciation for the likelihood of having 1, 2, 3 multiple solutions. It's based on the basic knowledge or the foundational laws that govern the system that you're looking at. Alright? So you must know that. So you should know if you should be looking for more than one solution. You hearing me? So you can't. You say you can't appreciate that. I've said it. I think I said this in the original class. The computer is a aid. You can't make it a master. You can't make it tell you. You must tell it what it's saying. Okay, it can't tell you what to say. You must tell it what it's saying. You must make sense of what it's saying. Alright? So you should know that there are other solutions based on your knowledge of the field that you are looking at. Alright? So here's another case, a terrifying case. Case E. You have a quadratic. It's still one solution. They still call it 2 roots though. Okay? And this is another terrifying one. It's actually called 3 roots, all being that the 3 are the same. And here's a wickeder one. 3 roots where 2 of them are the same. And here you have multiple solutions. Here's one in which you have 2 roots at a point, and so on. So again, the important thing is that you know your general understanding of your physical system, so you should know how many solutions you should be getting. Don't completely count on mathematics to tell you what is happening. You must understand the physical world or the physical system that you're modeling also. Alright? Okay, so we're going to first look at root finding, and then we're going to look at fixed point. Most of the iterative procedures are what we call root finding. Okay, fixed point is actually rare. There's only one method of fixed point. I'll discuss again the difference between a fixed point problem and a root problem. Almost all iterative procedures are root finding versus fixed point finding. So sometimes a textbook will just call the whole chapter, instead of calling it iteration, it calls it root finding, because root finding dominates the iteration procedure. Question? No question? Okay. Alright, so based on what I've said so far, bounding, you must. Okay, I won't discuss the first statement. When we get to it, you'll understand. Everybody should be clear. Good initial guesses are very important. Closed domains are robust. That means you're sure to get the answer when you use a closed system where you bound it. Open domains are faster, but they are more faster, but what should I say? They're more damaging if they're wrong. Okay. Note, complex roots must be anticipated. So sometimes you may have the square root of a negative number in your system and all them something there, or some odd math. How can you anticipate something? You anticipate it because you understand the physical world that you're trying to model and solve. So I can't tell you what to anticipate in your problem. You must understand your physical world, and in your physical world you should understand that this is a possible answer, or this is a possible solution. So if there's a root that's an answer, or complex root, that's especially in the electrical world, then you know to expect that. Right? You must always balance the use of the computer versus the use of the human brain. Alright, you must know to what degree you want to repeat a procedure. If you want to repeat it many times, then you're going to more base it on the use of the computer. But if it's not too many times, then the initial guess becomes more important, and the human effort in coming up with that initial guess becomes more important, right? We're going to learn especially two methods called the Newton and the secant. Those are very important root finding methods. Alright? Okay, let's go through the procedure of root finding methods. Remember, these are computational algorithms that you're going to program. So now these are when we say algorithm, the term here algorithm, what I mean is here algorithm, what I'm talking now is the program or the computer code to do the iteration. Alright? Everybody following? Okay.
Yes, we are.
So algorithms.
Following.
Yeah, so algorithms is the computer code. Alright, your computer code must always have a limit on the number of iterations. Limit meaning you're going to be searching for something. Just like if you were searching for a ring in the grass, you'll say, I will search until night come down. You can't say, I will search until I find it. Understand? If you say that you'll search until you find it, then you will crash. Computer will crash. And you will take up cold in the night. Night you will drop on your head. I hope you understand me, I say. So you must put an upper limit. In the computer world, the upper limit is the number of iterations. For example, you may say if n equal 100, or if n greater than 100, break the sequence. That means stop searching. When you reach the maximum number of iterations, you have not reached your answer. Okay? When you reach the maximum number of iterations, what you have done is you have said, I am not finding my answer. I need to come up with a new initial guess. Everybody clear?
Understand.
Next, you must check if your solution, when you find the root, confirm that the slope of your root is not close to 0. What does that mean? Case E. Everybody see case E? Suppose you find your solution at case E. You should be able, remember I said, for example, when you're looking at case C here, I said if you knew that you're sloping up, then you know that the other root is to the left. Or if you're sloping down, you know that the other root is to the right. For case E, what you know is that you get to the root and you say, aha, I found the root. You must check what the slope of your root is. If the slope of your root is 0, then you actually found 2 roots. The 2 roots are the same value, but it's 2 roots. Alright? I know it sounds odd, but it's actually 2 roots. Okay? Next, the other way to stop an iterative procedure, the first way to stop it is you get tired, or the computer get tired, so you say, I can't look no longer. When you reach that point, you don't say you find the answer. That's a lazy man. Lazy man go till him tired and then he say find the answer. I can't go no longer. Alright, but you have the other case where you can say you found the answer. You find your answer if your solutions are approaching an acceptable error. Okay, so that's the second way you stop an iterative procedure, when you realize your solution is approaching the answer, the exact answer. And finally, it's always wise and healthy to take the answer that you say you're sure you got and plug it into the original question. Remember that the algorithm may not have had the function in its original form. You may have done some manipulation of your function before you put it in the algorithm. So after you've done all the computation and you say you get your answer, then go back to the original problem and plug it in to confirm that you did find the true answer and you didn't find some trivial answer. Alright, a trivial answer is an answer that mathematically is correct, but practically speaking is irrelevant. That's what we call a trivial answer. Okay? Okay, so let's go into the procedures. Everybody okay? I have been meeting once every 2 weeks. We may now have to increase our pace. So I'm thinking we'll just start meeting once a week. Is that okay with everyone? One reason why I cut back was,
Yes, sir.
one reason I cut back originally is a large segment of the class. That's the older set. It's actually 2 sets. So the older set, we're finishing another module. That module was finished last week, and so they have a little bit more time to commit to this. I'm not going to overwork you guys, but it's just to keep the material fresh in your minds. Alright? Okay?
Okay, so
Alright. What time is it? Anybody can tell me the time?
8 o'clock.
4:08, sir.
Alright, let's go for about half or more. I'm not going to go through all of this topic, but I'm going to go to the first types of iteration, and you'll have some little assignments to get you you know, warmed up in terms of iterative procedures. Alright, and then we meet next week and we finish off iterative procedures. Okay. Alright, so we're going to first do the domained or the bracketed methods. Remember, almost all these methods will be root finding, except one, which will be fixed point. Let me go back, show you something. Here are the different types of iterations that we'll cover. Every one, you see how many here? 6 of them. So note, of the 6, these 5 are all sorry, mistake. These five are root finding. This one is fixed point. Okay, when we're discussing that, we'll make it clear what fixed point is. I think I've said it a few times already, but not sure everybody get it. Okay, so root finding methods, one is called bisection, the other one is called regular falsi. Here's what I'm going to do. I'm going to put a blank slide in this so we can work on it. Blank slide. Hold on here. Yeah, come. Give me a minute. Alright, so let's go to a blank slide. So what we have is I'm going to draw a system. Everybody's seeing this, right?
Yes, sir.
Yes, sir.
And here's our function. We'll say this function is a function of x, y. Okay, so here is our answer here, but let us say we don't know that's our answer. We have something called bracketing. First option is called bisection. What is bisection? It's a case in which you determine, let's say you know that your root is between x equals 0 and x equal whatever this is. You know, it's somewhere in that range. This is your range, right? You want to know where is it, where is your answer. The procedure of bisection is start out with your original range, then you're going to break it into two. Oh, first of all, you calculate the y's for both of these. So my first y this y is going to be that value, it's a negative value, and this y is going to be a positive value. Whenever you do bisection, the bounds must be of the answer for the bounds must be of different signs. Okay, so that means whatever I pick for my initial x's, remember it must be two values for bounded problems, so your guesses are two values. One guess must give you a negative value. Remember, the root is to determine the x that gives you 0. So you're going to pick two values, two x's that give you, one must be a positive value and one must be a negative value. Okay, of course you're never going to pick the x that will give you 0. That's what you want to find. But you're going to pick two x's, one that give you a negative value and one that give you a positive value. How would you pick those two x's? Just recall the different ways of doing initial guesses that we did earlier. Alright, so so your two initial guesses you solve. Then what you're going to do is you're going to split the domain in a half. Let's say this is where the half mark is, and for that half mark you're going to solve the function. In this case, when you solve the function, you're going to get a, what is the positive or negative value for the function? Hello?
Positive value.
Positive value. Good. So this is now your first iteration step. You found a positive value. What you want to do is you now want to discard one of your old bounds. So this is your original bound, right? Now you have to reduce your bound. Your bound must be either reduced to this half of the system or that half of the system. Which one would it be? Half A or half B?
Half B.
Half B. Good. So the criteria for determining which one you would use is simply what is the sign of the new bound. Whatever the sign is, then this bound will become one of the new bounds, and you're going to discard the bound that has the same sign. So for example, you have two other bounds, this one and this one. Which one is also positive? This one is a positive one, right? So you're going to discard this one, and so now these two are going to be the new two bounds. Okay, so this is now your new bound. Again, you split that bound in a half. You calculate your function. Now your function is a
Negative.
good. Since your function is negative, you're going to discard the one of the previous bounds that was negative. Which one of those bounds was it? Was it bound 1 or bound 2? Which one is the negative bound?
2.
Bound 2. So you discard bound 2, and so now the new bound, I'm going to call it bound 3, is going to be one of the bounds, and bound 1 will be the other bound. So now your range now has changed to that, and as you can see, every time you half it, you're getting closer and closer to the answer. So if I half it again, I'll be there, and if I half it again, I'll be here, and if I half it again, I'll be here, and then I'll probably half it there until I get to my answer. Okay, that's bisection. clear?
Yes, sir, that's clear.
Just wondering though, sir, how you determine when it's negative.
How do you do
I got it from the point where you said the A and the B.
No, you don't say is the function greater than 0. That's all.
Okay, cool.
That's all. I'm going to give you a few exercises in MATLAB so you can learn some of the little tricks. Alright? So it's all here. So you have your function in the root form. What you're going to do is you're going to pick a value for x and find the function. Make sure that your initial two x's, one will give you a positive and the other one gives you a negative. Okay? Calculate the midpoint. We use the laser. So here you have the midpoint. Calculate the midpoint. If the midpoint is greater than 0, then that midpoint becomes the new positive side, and you discard the other positive. If the midpoint is less than 0, then that midpoint becomes the new negative side, and you discard the old negative. Understand? And you repeat until you get to your answer. I won't go through the example. You want me to go through the example?
Yes, please.
Okay, I'm going to go through the example on MATLAB, on Octave. Alright? A script. Good. So let's go over to Octave. I want everybody to confirm that you're seeing it when I open it, alright? Everybody seeing Octave?
Yes, sir.
Alright, good.
Yes.
Alright, so I want to find the square root. Let's see what the question. Okay, x equals square root of 2. What is the root form of that expression?
Repeat that?
What is the root form of this expression? We have
1.41.
No, that's the answer. What's the root form? What's the root form?
In Octave?
No. Okay. It's a good question because so it tells me to know. Root form means a form in this form. The function is equal to 0. So how can you express this in that way?
X minus root 2 equals 0.
Good. X minus root 2 equals 0. Everybody can appreciate, however, that the problem is you may have a situation you don't have a calculator to calculate root 2. So a better option for the root form is x squared minus 2 equals 0. Everybody hearing me?
Yes, sir.
Yes, sir.
Note, however, this has two solutions.
Yeah, because it's a quadratic.
Right. Hold on, sorry. It has two solutions. but the original problem has one solution. Okay?
Yes, sir.
Yes.
So that's an example of saying you must know what your system is and you must know what your legitimate answers are. Alright? Anyway, this expression f of x is equal to this. This is how it looks. Just in case you never know. Oops, sorry. Let me erase that. Do it again. Let me put it on the blank slide. Blank slide. Go back to the blank slide. And clean off this slide. Okay, so that is what this expression sort of looks like, okay? And what we want to know is we want to find this x here, what this point is. So you see how a graph can help? Not that I need to know the exact value of the graph, but I have an idea of the behavior of the system. Why does it keep putting that little thing there? Everybody clear? How a graph can help you to do bounds?
Yes.
So we know the answer is here. So to do the bound, I can simply say, okay, I'm going to make one of the bounds 0 and the other bound, let's say 10. I just know it's a large number. Or I can make the other bound, I won't say 10. Just look back at the original problem. The original problem is x equals the square root of 2. That's the original problem, right? So I could say I'll go up to 4 because I know that 4 is larger. Because I know that the square root of 4 is 2, right? I'm using that as an example. I'm going to go up to 4. So my original bounds is x plus is equal to 4 and x minus is equal to 0. Am I everybody clear on the initial guess?
Yes.
Alright, so let's start it. So I'm gonna call it x.
Sir, I think somebody wanted to repeat.
Oh.
So repeat that is initial guess.
Okay, initial guess. What I said is just by looking on the graph, I know that okay, y equal x squared looks like this. Y equal x squared minus 2 means you're going to shift down by minus 2. That means this is now minus 2. Okay? So we have an idea of how the system will look. Now what we don't know is the exact values here, where it crosses the root. Alright? So we say what we do know is our answer, we want the positive part of our answer. We don't want the negative part of the answer. The negative part is not representative of the original problem. Okay? The square root of 2 is not going to give me a negative number. No, following me?
Yes, sir.
Alright.
Yes, sir.
Alright, so
Yes.
alright, so what we're going to do now, we say we want just the positive answer. So it's starting at, it's one bound is 0, and we definitely just want to know we pass this point. Alright, now we know that the answer is going to be less than the square root of 4. Yeah, the square root of 2 must be less than the square root of 4, right?
Yeah.
Yes, sir.
Okay, so if x was equal to 4, if x was equal to 4, we know that we would get, let's look at the original function. Where's our original function? Let's write it here. Original function is x squared minus 2 equals 0. If x equals 0, the function equals minus 2. Everybody see it? If x equals 0, the function is minus 2. And if
Yes.
Yes, sir.
x equal 4, the function is 4 squared, which is
60 minus 2
14.
good. What I'm saying is we have two values. One of them is positive and one of them is negative. Understand?
Yes, sir.
Alright, good.
Yes.
So let's see if we can write the procedure here. I'm doing it very crudely. So I'm going to say x, let me call it n. No, I want to plot. I want to use a symbol for the minimum x and the maximum x. Alright, let me just type out the whole thing. X min equals 0, x max equal 4, and then I'm going to go into a loop. Okay, so I'm going to say error equals 1, and then I'll say while error is greater than 0.01, I'm going into a while loop. You see, when I press enter here, nothing will happen because it won't do anything until I finish saying everything in the while. Okay, so while error is greater than, that means 1% error. Let me do another one. So I'm now in my while loop. I'm going to say x mid equals let me write the functions first. f min equals, what was the function? X min
Squared minus 4.
Squared minus 2.
squared minus 2 f max equal x max squared minus 2, and I'll say x mid equal x mid equals x
max
right
plus M min.
right, that's it, the middle, right? Then I say f mid equal x mid squared minus 2, right? Then I say if hold on, a moment please. Yes,
Sir, check over the line that says F min. Is that an equal sign or a minus sign?
it's a equal, man. It's probably the zoom on your it probably does not zoom in well on yours, right?
Okay.
You want me to zoom more so you can see it clearly? Or is most people
No, man, that's fine.
most people are seeing it, right?
Minus 2. For the f min minus x min to the power 2, that one look like minus 2 min too.
Okay. Yeah, man, the other saying is f mid equals, but you're saying it look like minus to you. Yeah, don't worry about it.
Under the while error, it looks like f min minus x min to the
Okay.
power 2 minus 2.
Okay. Yeah. It's equal.
Okay.
Alright, so note the if. So I'm going to say if if f mid, oh sorry, if f mid is greater than 0, then I press enter, and then I state what I want under this condition, right? So what do I want under this condition? I want x, if it's greater than 0, then I want x max okay to be equal to x mid. Everybody remember that? I'm going to discard the whole x mid. I'm going to replace it with not x, yes, I'm going to discard the whole x max and replace it with x mid, right?
Yeah.
And then I say Then I'll say else, and after else I put x min equal x mid. Alright? Then I say end if. That's the way you come out of an if statement. Alright?
But sir, in that case, when you're coming out of an if statement, you have to put end if, can't put end alone.
No, I think MATLAB uses, I'm not sure, I think lately they are changing how they do the ends. They used to say just end, but now they start doing different ends. So they say end if, end while, end for, and so forth. But all you do, just check what the syntax is that your system uses. Okay?
Alright.
There for the octave, I find that end ends the while and if and else. But
Yeah, man.
it shows you where you're ending the if statement or you're ending the while statement, so you don't get confused.
Right. Everybody heard that? So the end still works, right?
Yes, it does.
So end works, but it's just to remove all doubt. For example, in this case, we have if and a while, if within the while. So just so you don't confuse yourself, when you put f in, f end if, you know that it's not closing the while, it's closing the if. Understand?
Sir. Yes, sir. You can indent while using the.
No, I can't indent. I could put some space bars. I can just put spaces, but I can't indent while I'm in the command window.
Okay, sir.
Alright. Well, what I'll do, I'm going to copy this over to a script. You want me to do it all on the script file?
Yes, sir.
Alright. I'm going to still go run it, and then I'll copy it over to the script file and run it from the script file. Okay? So end if. After I end if, I'm going to say error equals absolute hold on. How would that sing? How would that sing?
You have to check the mic, because sometimes my mic just turn on.
So you are singing to that?
No, let me sing my. Sound like a bandista singing a bandista all going.
Alright, so
Oh,
error.
it's a problem, man.
I shouldn't have said error, but it's alright, we'll work with it. Error equals, and we'll say, this is always how you do error. It's the absolute, yeah.
Why you shouldn't have said error?
No, just in case, it's fine, but just in, you see, whenever you have a common statement, like the word error is something that I can imagine MATLAB or Octave may reserve that word for things.
Okay, sir. That's why I'm going to drop off one of the error from my own, sir, just in case.
Okay. So it would be x, any one of them, doesn't matter which one, x max minus x mid over x, any one, mid, not min, over x max. So when we do that, so we calculate the error, and then I now can say end while. Everybody agree that this will work? Should work?
Yes, it should. It should.
So I do the end while. That's it. It's did it. But it's not right. While error is greater. So why is my, oh, see my mistake? So it picked.
A colon between the 0.00.
No man, the error is, the error was that in my case I should have said x min mid max minus mid. I should have kept it as max minus mid rather than max minus mid, because sometimes these will be the same. Okay?
Okay.
So what I'll do is I'll copy this over to the editor.
Copy. Yes, sir. That's what I was saying.
And just redo it, okay? Now it will I can indent also the editor So I'm going to say max minus min, and I'll call the, everybody's seeing the editor, right?
Yes.
Yes.
And I'll save this as hold on. You don't need to see my files. And this is called bisection, right? And what I did is I went into this unit or this this folder. Everybody see where I change the folder? Alright, and I named the file bisection. Everybody see that?
Yes, sir.
So now in the command window I'm just going to type the word bisection, alright? It will look in the current folder, which is up here, which is where I saved it. Okay, first error. Line 16. Let's see. Oh, this shouldn't be here. Why did I have this here? I don't know. Let's save that again. Let's run it again. Alright, so it did it this time. So let's see what they said x is. So not x, x mid. that close to it? Close enough, right? Hello. How come nobody answer me?
Yes, sir. Close enough. Because you said the error, right? So probably if you increase the error margin, then it'll be more precise.
Right. So let's increase the error margin by 100. Let's put 2 more zeros. Run it again. And let's see what is now x mid. Same thing, right?
Yep.
So that's a bisection method. You learn something. Every operation that a computer does is only the basic 4 operations. That is addition, subtraction, division, and multiplication. Those are what we call the basic operations. Every other function known to man, mathematicians have found out how to use those 4 operations to do every other operation or function. For example, I just did the square root. How did I actually calculate the square root? Just by using addition, subtraction, multiplication, or division. If I want to find the cosine or the natural log or some mad power, I can still use those basic 4. Okay?
Those are also the basic 4 that your processor uses.
Right. That is the basic 4. What your computer languages have done is that they have functionalized some of them, some operations. So, you know, some things that are repeated, like a trig function or a power or something, or a log function or a hyperbolic function or whatever it is. It's so repeated that it's now programmed into the system, so you don't have to keep reprogramming those steps. Alright, so that's it for bisection. Note, this is the basic step right here. What I could have done, this is the function statement, right? Everybody said this is the root form of the function. I could have called a function called f. So we can make a function, and I could have said f min equals f. Let me call it fu. Let me call it root f. The root function x min I could have done this x max. I could have done this x mid. What would those do instead? Can anybody tell me what those would do? Hey, look. Nobody there?
Yes, sir. Just thinking about it.
Okay. Give me some time.
just use the original equation? Would that function now draw from the original equation where x was equal to the root of 2?
Right. So what you'd have to do is you'd have to have another equation which I'll call root. So this is called a function now. It's a function file. Okay? Function. Then I'd say y equal, and this is where I give it the name, so I give it back the same name. Same name is root f. Root f. I'm going to root f x. Okay, and then here you'll say y equal x squared minus 2, and then I say end. I could also say end function. Everybody clear?
Yes, sir.
Now I'm going to save this. I'll call it root f and I'll run bisection again.
There, I don't think the roots is going to work. I think you have to do root capital S roots.
Repeat what you just said.
I think it has to be root with a capital S roots.
Here?
Yes.
No man, I'm the one who made this function, you know.
Okay.
So I made up a function called root f, and here's I'm defining the function. So this is the function that I want to calculate the root of. Okay, and now in bisection I call that function. I'm going to give you a little time to think it through and run it again, and let's see if we still get back the same answer. Let me show you what I'm trying to say. I could make the function the cube root. Let's say we're doing the cube root. Instead of going here and changing anything, I can just go here. We want to find the cube root. I change that to 3 because that would have been the cube root root form of the cube root of 2. Everybody clear? Suppose I said I want to find out x equal the cube root of 2. Instead of changing the bisection file, I just change this file. Everybody? Okay?
Understood. Yeah, makes sense.
Okay, so now let's see if it calculated it. Let's see if that's right. So 2 to the 1 over 3, right? So this is your basic. So what I have here is the basic bisection, almost basic. This is very general. The only way it is not absolutely general is right here. So I could have now made this a function that I call bisection, right? I'm going to make this a function, and I'm going to call it function y equal bisection I'll say bisect. because I'm not sure if bisection is a function already. Y equal bisect. No, let me say bisection. How you know if it's a function while you're typing it? If nothing comes up, then it's not a function. Everybody clear what I just said?
Yes, sir.
Yeah, we heard it.
Alright. So let me try. Let me just check. Help. Another way to check. You can type help bisection. Let us see. There's nothing in the system on bisection. So you can use that as a function name. So I say bisection, and I'm going to put the following: x min, x max, and error. I'm just going to call it not error. And then this means acceptable error. I'll always start with an error of 1. X min and x max now will be given x min and x max now will be given by the program, by the function, so I delete those. Hold on. I'm going to call this final error. So while error is less than the final error, you go through this, and I'll no longer call it error, I'll call it error. And I'll tab that, I'll tab that, tab that, tab that, tab that, tab that. Everybody see this now?
Yes, sir. Yeah.
So I'll save. Now, if I say bisection, it won't run, because it's a function and it's supposed to give some arguments. See that? So let's just make sure everything is okay. Good. So now I'll say bisection. What are the arguments in bisection? X min, so I'll put 0, 4, and the acceptable error. And now it runs. Okay? Only problem is that I don't get an answer. I have to tell the system to give me an answer, so hold on. It's a blunder here. So I must come out and say y equal x mid. Okay? You know, I don't like y, I think I prefer x, so I'll put x there. I'll put x there. So now, when I run bisection, everything is saved. Yep, run bisection. So I'll say x equal bisection, all of that, and there's our answer. Let me check something. Good. So that's it. So if I want to change my error, I change my error. If I want it even a little, everybody say I dropped the error.
Yes, sir.
If I want to change the function, let's say I want to find the fourth root. So now I have to change the function that's here. I change to the fourth root. Go back to the command window. So that's now the fourth root. So I just a check. How about 2 to the quarter? Same thing, right? Of course, my error is very crude. So if I wanted to improve my error, fourth root, see if I get back the same thing. Closer. If I want it to even be better, closer, still not exact. If I want it even better, and I get back the same thing as that. Alright. So what I've just done, I did a few exercises in this one period here. It's time for us to stop. It's 9 o'clock. The exercises, apart from doing the general bisection approach, what I did here is I actually wrote a bisection function. This bisection function is absolutely generic. That means it goes for any bisection problem you can have. There's nothing in this. You realize there's no number, nothing unique in this. It calls the function that you want. So that is where you put in the unique information. What would be unique information? The function, which is here. And the other unique information with the min and the max, which you would put in when you call the function, right? The min, the max, and the error. Alright? So we stop there. You'll probably now be able to breeze through the rest of next week Saturday when we meet. You'll kind of breeze through the rest. I thought I'd give you some experience or some practice, exposure to the use of the loop. The loop is very important. It's obvious that the loop is very important to iteration, right? Because that's what iteration is about, doing something over and over again. So there are several loops that you'll have to do. Yes?
Sorry, quickly, this that I just said, you'll put it to a screen or something for us as an example. That's it for practicing. You can something to guide us.
I'm recording all of this.
Oh yes, sorry, yeah, I forgot to record.
Yeah, I made a little blunder when I took a little 5-minute break. I stopped it. I didn't really erase it, so it's actually 2 videos you'll see. One before I took the break, and then one after I came back. Alright? I should have paused it.
Yes, sir, thanks.
I should have paused it. Well, I did pause it, but when I came back, I pressed the wrong button. I pressed the button to stop. I should have pressed the button to resume. So when I press the button to stop, I had to save the previous I think it was about a half hour, and then I started a new recording. All right. So that's it. I hope you guys are doing your assignment. That is the project. Let me check the groups. Did anybody, or Orlando, did you get to go in any group with anybody?
All the other groups are full, sir, barring the one that I'm in right now and the next one with Joe.
And I say me make a little plea for the man. Nobody not even show a little mercy, man.
Then you can join Paul's group.
Yeah, you can come in chemical processing in Orlando.
No, but I know say crab more than 4. That's why you know me that I take even 10 if it's possible.
Yeah, you can't go over 4 for a group, yeah? For proper group work. It's a little...
I mean, somebody would have 4 minus 6 days, sir.
Hmm?
There are 4 persons in my group.
Yes, I know. I'm looking at the groups again.
Okay.
See what you guys have. So the only empty groups are economic systems and urban planning. Which one you in, Jordan? The urban? I mean, Lando?
Urban.
Okay. I'm surprised there's some more people never want the urban.
Alright, so interesting.
Not true?
Sir, you have Dwight, Mr. Chance, go ahead, please, sir.
Yeah.
He's at NHD.
I know. I thought Dwight would do it. Or...
I kind of like the structures, actually.
Okay.
Urban would have been my second choice.
Yeah. Who doing environmental?
I'm going to be structured at first, but they vote me out. God will vote me.
Who doing environmental? Alright, let me look. I can see the members. So it's Brandis, Odian, Shanroy, Richard. And systems is Cleos. Oh, Sean is out. So Cleos, you're on your own in systems. Sean realized that you made a mistake. You shouldn't have been in this class. So you and Lando have to decide now.
Okay.
If you want the systems or if you want the urban.
Well, I'm staying with urban. I don't want to do systems analysis.
And you definitely want the systems, right?
Yeah, but I started early anyways. And I started early anyways.
Oh, you started, alright. So,
Alright, no problem. I can switch.
alright.
That's okay.
Alright. So urban is going to be, you can switch, just go online and move over to urban. And if there's anybody else in the other 5 groups, is there anybody else who may want to join the urban group, just feel free to consider that, okay? And the most likely persons would be those who are doing either structural or environmental, because those have urban elements to them, right? Can have urban elements. So yeah, just give it some thought, alright? Okay, but Cleos and Orlando, remember it's group work, so I'm gonna try and link up. I mean, when I say link up, it might just be online or such, but try and link up since you're kinda late starting getting connected with each other. Okay. Alright guys, so please give me some feedback on your work so far. Remember, it's not so much calculations, it's more a report and presentation. Of course I have to do presentations because I'm not saying you guys are disingenuous people, but in the modern world of IT and the internet, people just copy paste, and sometimes they don't even know what they copy and paste, and then they present it as their report. So when you do a presentation, it reinforces that you have actually gone through the content that you're reporting on. Everybody clear on that?
Yes, sir.
Yes, sir. Clear.
Okay, good. Alright. So you'll see another assignment. Nothing to be frightened about. Thank you for the recent submissions, and please keep working on your projects. Thank you very much.
Sure.
Yes? Yes?
Hello?
I'm hearing you.
For the assignment, yes. I didn't give him the printout
So on the thing, you still can go online and put it in.
No, I submit it online. But you wanted a physical printout?
No man, when you say printout, you know, it's printout means what would the computer print out? Or okay, everybody look on the screen right now. What I'm highlighting is a printout.
Oh,
Understand?
okay.
So that's what I mean by a printout. So when the person is at the command window and they print they type a command and then something comes out. So you would actually post everything what the person types and what the computer spits back out at you.
Okay.
So you would just copy and paste this. That's all I'm saying. Just copy.
So I did it from the editor.
Huh?
I did it from the editor.
You can do it from the editor, but you have to copy and paste this into something. So you could copy and then you go to an editor. It doesn't have to be this editor anymore. You go to an editor and you paste.
Yeah man, that's what I did.
Okay, that's fine.
So I actually copy mine and paste my Word document. You know, copy it from the script and also from the function.
Right.
And put it in Word.
Yeah man, Word is fine. All I hope that everybody recognizes in the assignment, I say please make sure that you use Courier font to identify your commands. Everybody saw that?
No sir, you never see that one.
No sir.
Anybody saw
Yeah, I
that?
did not see that.
Did anybody see it?
Maybe the new course.
Yes, I did say, is it a courier or no courier?
Okay. That was very much there, man. But anyway, now I'll kill you. I put those little things to see who reads things.
I wouldn't just say so.
Alright.
Sir,
Yeah.
sir, with regards to the project, according to the schedule, it's due this week coming, right?
Yes.
Is it possible for us to get like a week pushback? Seeing as how myself and Chaos
That's
kind of
all.
just form the group.
Alright. Oh, the other people don't want to take more time?
Of course, I need to answer the
Yes sir. Yes sir.
Everybody said they want more time. So, okay, so you tell me the time, Lando.
Huh?
So you tell me the time.
So I think a week will be good, right, guys? One more week.
So the 23rd of November.
For the written report?
Wait, hold on, sir. That means everything else I get pushed back or something.
Yeah, everything else I get pushed back, yes. We're still going to finish in December, though, you know. We're not push over into January.
Before that, sir.
Remember, I'm saying we're doubling up our meetings.
Okay.
Okay?
Yes, sir. So the 23rd for the report, right? And the
24th.
for the presentation?
Yes, right. Since
Okay.
we meet on Saturday, right?
Mm-hmm.
I will come in on that day, Lord willing. Okay?
Yes, sir.
I'm trying to get skilled on the online, but I don't think I'll figure out how to have you all do your presentations and we're all online doing that. I think there's a way, but I'm not going to push that a
Yes.
bit.
In charge of the presentation.
Huh?
If we're presenting via Skype, we'll just take over for the presentation.
Yeah,
Yeah,
it says request control.
Yeah, you can. So you don't want to do it online too? I'm
We can
actually,
do a test run.
All you
yeah.
have to do is just figure out how to make our document the primary.
Yeah.
Okay.
We'll
Okay.
test run like the day before if it don't work out with me in
Yeah,
person.
like
Like I'm asking.
Landa just sent a request to give him control, so I could say yes. I'll see how I do that. Are you using Skype web or Skype for business, Lando?
Think it's Skype. I don't know. It downloaded an app on my computer.
Okay, that's Skype. That's Skype web. It's a web app. It's a web app. Okay. So almost everybody is using the web app then, right?
No, I'm using Skype for business.
Okay, which would be more souped up. So alright. So I'm just confirming those who doing the web apps, you can. It's clear that you still can make the presentation because Lando just sent a request and I could have approved him to take over the presentation. Alright. So we meet again next Saturday. Alright, folks?
Okay, sir.
Thank you.
Thank you for your time.
Thank you.
And I think this online thing is getting better each time, isn't it? No bugs this time around.
Yes, I go good.
Alright, great. So we can officially say we do distance or online course of studies and so forth, not sure.
Yes. Because I'm happy thing that now record that.
Alright, boss. Later.